Well, hello and welcome back to the third Bootcamp segment on Python and its use in chemical engineering computing. We are going to take a look at two detailed examples in this workshop, and they're going to have to do with the modeling of chemical reactors. You can see the specifics here on the slide, what we're going to be looking at. And a primary purpose of this particular boot camp is to show how we can integrate and put together the elements that we introduced in the previous two, having to do with the Python programming language and also problem-solving techniques that we looked at a smaller scale, and integrate them, put them together in a more challenging modeling scenario. So this is what we're up to here. The files that we're going to be using are all available to you, as are these slides. And I hope that you will load the files and follow along with me and execute the files and try to appreciate how that is all put together. So to start out with, we're going to be looking at ammonia synthesis, and we've shown here a couple pictures of a packed bed ammonia reactor. It's got an iron-based catalyst in it, and one is being brought to a construction site. You can see it here on the left on a trailer with a couple of individuals standing off to the left. Give you an idea of the size that we're talking about. And then on the right, a reactor that's in place vertically. And we note there that ammonia is produced in very large quantities worldwide, 180 million metric tons per year. So as we look at the chemical reaction involved here, it's fairly simple. It's just nitrogen and hydrogen combined in stoichiometric ratio to produce ammonia. And it turns out that for this reaction, there's a forward path and a reverse path. And the reaction is run in gas phase, obviously, and at a very high pressure. So we have rate expressions for the forward and reverse reaction stated here in terms of partial pressures of the various components, and the reaction rate parameter is given by the Arrhenius expression in both cases, with a pre-exponential factor and with an activation energy. And you can note the units that we've adopted here might be a little bit unusual for you with the use of atmospheres, but that was typical from the basic data that we obtained. So there are the reaction kinetics that you're working with. And then what we want to do is assemble a mathematical model for the reactor, which is a packed bed reactor. So we denote that up here with feed rates of nitrogen and hydrogen. And actually in our model, we will have a couple of other components that are inert, that are typical to industrial mixtures. And then coming through the reactor of a given diameter and length, we come out with unconverted nitrogen and hydrogen plus ammonia. And it's well known that the conversion obtainable with one pass through the reactor is on the order of 20%. So the actual process here requires separation of the ammonia from the remaining nitrogen and hydrogen and recycling of that back to the feed so that you can have multiple conversion passes. So we describe our mathematical model here in terms of molar flows in a differential balance with volume down the reactor, and that's given by the disappearance of nitrogen by the forward pass of the reaction and plus the reverse path, and then times the void fraction, so that we're dealing here with the void volume of the reactor as we solve the model. And you've got some dimensional relationships down here relating the differential volume to the differential length and areas and volumes. And then once you have that, the model actually here is fairly simple, because if you know the feed flows of nitrogen and hydrogen, you can get the flows of hydrogen at any point in the reactor via stoichiometry, given the amount of nitrogen that has been consumed, times 3. And then you can also get the flow of ammonia by the amount of nitrogen that has been converted, times 2. So those are the balances. And then we get into the details of the model, because we have to consider the energy balance. And the basic energy balance that we use here is that enthalpy is conserved, so that the differential or change in enthalpy as you go down the reactor is 0. And if you make a common approximation here, you can come up with, let's come forward. Come up with, by assuming a constant heat capacity, you can come up with a differential of temperature with respect to volume, where because the heat capacity is constant, this summation term would be up here on the left side, and you can bring it into the denominator. And then you can then use the heat of reaction as the change in enthalpy, and it's an exothermic reaction here, and it's a function of temperature and pressure, and again times our void fraction. So that's the simplified energy balance. And then the one thing that we have to consider for this particular reaction is the pressure effect on enthalpy. We need to keep that in mind. For a simplified model, this may not be important if we assume a constant pressure down the reactor, but we see it here, which is given by the integral of the heat capacity over temperature. But then we have the integral over pressure, all right, the pressure effect on enthalpy, and then we have the initial enthalpy for that, feed enthalpy for that component. And we can express this integral in terms of an average heat capacity times a delta T. And then the integral on pressure here, all right, we can get that from an equation of state, possibly analytically, or from actual data, or using something called a generalized Pitzer correlation. So keep that, that's your slide for the energy balance. And then we see if we're going to model pressure drop. And here, a common equation used to model pressure drop through packed beds is the Ergun equation, and it's given in this somewhat complex form. The one parameter in here, mass flow rate per unit cross-sectional area of an empty bed, is constant with volume as we mow down the bed, so that's something that we can determine. And then the rest of the nomenclature is listed over here. And we are able to differentiate this in terms of pressure to obtain a differential equation for pressure as we go down the bed, and that is noted here. If we make an assumption of constant pressure or negligible pressure drop going down the bed, then we don't have to deal with this particular equation. And so let's put together a couple of other needed pieces of information. And one is the fluid density, which we're going to need if we deal with the Ergun equation here. And the fluid density is given by an average molecular weight divided by a specific volume. And here we're going to come up with the specific volume from the Peng-Robinson equation of state, because again, we deal with elevated pressures here. And the Peng-Robinson equation of state in terms of specific volume is given here. It's a cubic equation of state for specific volume, so it has to be solved. And A and B here are mixture coefficients, all right, given the composition that we have. We're not talking about a pure component. And we could try to use the ideal gas law as a simplification, but if we're operating at 150 atmospheres, then we're going to be off by about 20% here, so that's not something that we would want to do. So to get the mixture coefficients from the Peng-Robinson equation of state, we can get the individual coefficients from these two relationships involving critical properties of the components, and the factor here based on acentric factor for the component I. And then if X are our mole fractions, all right, a vector of our mole fractions, we can get our mixture coefficients using this matrix here, all right, which involves K parameters, all right, mixture coefficient parameters, which are available. And then we can get the A mixture coefficients using a quadratic product here with our mole fractions, and then the B coefficients using the mole fractions, all right, times the individual coefficients from up here. So that's a way that we can come up with what we need for the mixture coefficients. And then if we try to put this together into a model, we're going to take two approaches here. One is to use a simplified model for constant heat capacity and pressure. And then after we've done that, we'll move on to what we call a full model that includes all of the elements that we have described here. So let's move on and take a look at a information flow diagram for the simplified model. And it's not too bad. We've got our main differential equation for the flow of nitrogen here. And then we use this symbol to indicate that we're integrating or solving the equation, which provides us with values of the flow. And then with that in hand, we can use our stoichiometry to come up with the current flows of hydrogen and nitrogen. We can then add these together to get a total flow, all right? And then if we're assuming constant pressure, P, we can use the flows over the total flow times the constant pressure to get the partial pressures. And we can feed the partial pressures back into our rate expressions, assuming that we have a value for the temperature. And the temperature comes from our simplified energy balance, which is integrated, all right, to give us the temperature. And all these elements are available, all right, given that we have data or a correlation for the heat of reaction as a function of temperature and pressure. So this is the simplified model. Now what we want to do is show you how we put that together into a Python script, okay? So we're going to pop over to the Spider editor here, and we're going to take a look at the main script, all right? And then after we look at the main script, we'll look at the various components. One comment I'll make here is when you're developing longer scripts in Python and in any programming scheme, it's important to break things down in a modular fashion, and you will see that we have done that here. First, I'm going to comment as we go through here that we are including NumPy and we're including matplotlib for making plots, and then we're including solve IVP, our routine for solving initial value problems, differential equations. But we're also including here a separate routine for computing the heat capacities, and we'll show you that. And then we have a separate routine that we have to compute our derivatives that is required by the solve IVP routine. So for starters here, what we do is we just put together basic data, gas law constant, molecular weights, and then we have a set of coefficients for calculating heat capacity at 150 atmospheres. And in this case, we actually develop these by using the HYSYS properties package and then coming up with statistical fits for the heat capacity. And each one of these rows here corresponds to a different component. And you'll notice that we're including here inerts that are part of our feed mixture, which is argon and methane. So we come down here and we pick, in order to estimate constant heat capacity, we pick somewhat of a mid-range temperature for the operation of this reaction, which is 350 Celsius. And then we go into our heat cap function, which is a separate file, to calculate our heat capacity estimates for our mid-range temperatures. And the CPCOEF is this array of parameters here. And then the 1, 2, 3, 4, 5 are codes for our components: nitrogen, hydrogen, ammonia, argon, and methane. Coming on down and building on this, we put in our kinetic parameters here for the forward reverse reaction. We put in reactor size parameters and also the catalyst particle size and a void fraction. And then we get to our operating conditions. We establish our feeds here, and then we have our feed pressure, which we're going to allow to remain constant, and we have our feed temperature, which is 270 Celsius. From here, the setup is similar to what we've done before in solving differential equations. We have two differential equations, so we assemble an array of our initial conditions, and then we say that we're going to solve that from 0 to the volume of the reactor, and we've set the volume of the reactor up here based on a length of 1 meter and a diameter of 3 meters. And then we say we'd like to see solutions for 200 points as we go from 0 to VR. That's our V eval variable. And here we form the statement that allows solve IVP to develop our numerical solution. And you'll notice the first argument is something called PBR simplified, and that is our routine that computes the derivatives of flow, nitrogen, and temperature. Here's our V-span, 0 to VR, our initial conditions, our intervals where we're going to save the solution. And then we have a fairly long list of arguments that represent operating conditions and basic data that we want to pass through solve IVP to our PBR simplified routine. So we add them in an args list to the end of our call of the solve IVP function. And when it's done, we come out at the end here and we get our individual volumes going down the reaction from the T parameter in our result object. And then we get our flow of nitrogen as the first dependent variable solution. That would be index 0 and all of its values. And then we calculate the flows of hydrogen and nitrogen from stoichiometry. And then we extract the temperatures, all right, into a T array. We compute the conversion on a nitrogen basis and do so and produce it in terms of temperature. And then we create several plots to show the temperature profile, the component flow profile, the conversion profile, and then we print out a couple of results at the end in terms of the exit conversion and the exit temperature. So that's what this routine looks like. You can see, what do we have? We have almost 100 lines, take away a few spaces, a few less. And then as we look at that, then we can move on and we can take a look at the routine that computes the derivatives, which is called PBR simplified. And here we're importing another routine that is called heat of reaction. That's going to compute our heat of reaction from a separate routine. So we're keeping this modular. And again, we come in and do our gas law constant. And then we extract the current values from the y vector of the flow of nitrogen and our temperature. And here what we're doing is we're following the information flow diagram that we described to you before. We have that back here, all right? We're following that and putting together the derivatives. So here's our stoichiometric relationships, our total flow, our partial pressures, our rate constants based on our Arrhenius descriptions and partial pressures. And then we develop a two-dimensional, two-element array for the derivatives. And here, these are the expressions from the information flow diagrams for the derivative of the flow of nitrogen. Here we get our heat of reaction from our supplementary function, which you'll see in a moment. And then this is our calculation of our derivative of temperature. And then we return that, and that's what this particular routine does for us. So now we'll take a look at the heat capacity function, which is fairly simple. And it comes in with a component number, and then because of zero indexing, it takes one away from that. So we get our coefficients A through E from index 0 through 4 of our component, all right? This gives us our A through E, and then we come down here from the CP CoEF two-dimensional array. We calculate the temperature in kelvins, scale that by 1,000, because that's what was used to develop our equations for heat capacity, and then we use our equation for that component to calculate the heat capacity, all right? And one of the reasons that we use this divide by 1,000 is that's the typical thing that's done in correlations from NIST, and it was convenient when we fit the heat capacity versus temperature statistically to avoid numerical problems. Okay, so that's that, and then we look at the heat of reaction, and here we just have coefficients, and again, temperature in kelvins divided by 1,000, put that into a fourth order equation, and it comes back. And you'll notice here that because we developed this at 150 atmospheres, we don't have to make an adjustment for pressure because we're operating or assuming constant pressure. Okay, now when you put together routines like this, before you actually put them into your main scripts and run them, it's good to test them out separately and make sure that your results make sense. So we're showing here, and we'll show slides for in a minute. This is a test routine. It's called test heat cap. And it imports the heat cap function. And what it does is it just goes down through, and for temperatures here from 250 to 500 Celsius, it builds up an array, starting with an empty array, using the append method. It builds up an array of heat capacities that we can then plot and take a look at the plot and see whether or not they make sense. And likewise, we have a routine that tests heat capacity, heat of reaction, over the same range of temperature, and we can compute those, and here we can make a plot of them. And the purpose of this is just to test your separate functions independently to make sure that they seem to be valid before you put them into the overall. So let's come back to our slides for a minute and review what we've done here. This, again, is just showing you the first lines of the main script, which is available as ammonia.py. And then we move on, and we have the part where we solve the differential equations and unpack the results. We reviewed that with you. And then we have the final part where we create plots, and you've seen the scheme for doing that in the previous boot camps for this particular series. And then we have our PBR simplified. our routine that computes the derivatives, all right? We reviewed that with you. And then these are the two supporting functions for heat capacity and heat of reaction. Now, having done that, we can pop back over to Python script. And for instance, we can run our routine to test the heat capacity. And here is the result over here, and it shows us the heat capacity in kilojoules per kilomole Kelvin, and it shows them color-coded for the different components. And you can see that for the lower three here, all right, which would be nitrogen and hydrogen and argon, there's not that much change in heat capacity over this range. But for our methane and our ammonia, we have somewhat of a change of heat capacity. So that sort of gives us a little bit of doubt in terms of our assumption of constant heat capacity. But we can look at these numbers, perhaps compare them to some values from a handbook or from the internet and see whether they make sense to validate our routine. And then if we come to our test heat reaction script, we can run that, and it gives us a curve of our exothermic heat of reaction in kilojoules per kilomole over our range of temperature 250 to 500. And that range sort of encompasses the entire range of temperature change that we would expect to see in the reactor. And we can look at that curve, we could compare it to some values and just validate it, all right? And then we can come back to our ammonia main script, all right? And it would, of course, be the case most of the time that this would require some debugging. So I just want to mention one technique here that one can use as you go through this. Obviously, you can look at your variable explorer and you can look at all your variables and see whether they make sense. You can also single step the code, all right, as you go through, and we've shown you how to do that before. But you are not going to be able to single step through the solve IVP routine that it would make any sense to you. So one of the ways that we suggest of checking things out is to go to your routine that computes the derivatives and to put in a breakpoint at the last statement there. And what should happen then is as we run the solution, it should stop on that line the very first time that it goes through and it evaluates all the derivatives. Now let's see what happens when we do that. I cleared the variable explorer here, and let's come back, all right, and let us debug the file. And it comes in, and we'll continue execution to the next breakpoint. And here it stops here, and we can come over and we can examine all of our values and check them out. And in particular, we can be interested in our derivatives, all right, for flow of nitrogen. It shows it being consumed, and that would be kmoles per second per meter cubed, and then it shows the temperature increasing at a rate of 58.6. kelvins or Celsius. So we can examine these things and make sure that they make sense, and go back and make corrections. And you can put breakpoints elsewhere too. You could put a breakpoint up at the top of this, like here, and then you could single step this routine and watch your variables evolve and try to pick up where you think there are any errors. And one of the common things you would find if you had mistakes is that one of these derivatives would look way, way out of range that you would expect. Okay, so let's stop that debugging here and let's get rid of this breakpoint, okay? And assume that I've done all the hard work to debug this, and come back, bring our plots over, and let's run the script and see what happens. Okay, so what we've got here are 3 plots. The first is a temperature profile that shows us starting at about 270 and rising quickly up to about 375 or so. Here it shows 376.3, and then flattening out. And then if we take a look at our second plot, it shows the molar profiles for our 3 components. And so you can see most of the change is taking place here in the initial part of the reactor, all right? It's pretty much done by about 4 cubic meters, all right? And then we can take a look at our conversion profile, and it shows again the conversion rising quickly and flattening off at about 22%, as you can see with our output down here. So that represents the development and running of the model for the simplified model of the ammonia reactor. What we're going to move to next is we're going to take a look at our full model where we remove those simplifying assumptions, and then we can come back and we can consider whether going to the full model was actually required or not. In other words, are the approximations in these results sufficient for the work that we're doing? So let's pop back over to our slides. And this was the slide for the heat capacity function test that we went over with you. This is the one for the heat of reaction function test. And then these are the temperature and the conversion profiles from running the model. And then this is the molar flow profiles, and showing the results at the bottom for our exit temperature and our exit conversion. And the exit conversion of around 22% is pretty well established in the literature for ammonia, running at these reaction conditions with the appropriate catalyst in a packed bed. So what we'll do now is we'll take a little break, and then we're going to come back and do the second part of this reactor where we take a look at the full model. Let's continue and look at the full model for the ammonia reactor. And this information flow diagram's a little more complicated than the one we had before. The parts of it are very similar, such as the upper part. So let's look at this, and then we'll move on into strategies for solving the model. First, we've got the same differential equation for our flow of nitrogen, and the same stoichiometry for our hydrogen and ammonia flows. Total flow is the same. The calculation of the Partial pressure is the same, with the exception that the pressure here, the total pressure, is no longer constant. And then the kinetics up here is exactly the same as it was before. So because we're removing the assumption of constant heat capacity, we do not have a differential equation anymore for the temperature. Rather, we have an enthalpy balance where we take advantage of the fact that the total enthalpy does not change going down the reactor. And so we have a relationship here that the enthalpy at any point in the reactor is equal to the initial enthalpy. But you'll notice with this box, we put a double line on the ends of the box. And that is to indicate that this is what is called an algebraic loop or an implicit algebraic relationship. And in this case, we need to solve this relationship for the temperature. That's how we get the temperature. Then, and we'll get into that in a moment, and the temperature can then be supplied for the kinetic relationships. And then we come to the question of the pressure drop. And here we have the differential equation for the air gun equation for pressure drop with respect to volume. And we look at how do we supply all of the things required, all the items required on the right-hand side. Many of them are constants, such as the area here, the mass flow here, mass flow flux here, diameter of particle, etc. But some are not. And so in order to come up with this, we need to have the density, and the density is the average molecular weight over the specific volume. Now, the average molecular weight is fairly easily calculated once we have all the flows, total flow, and molecular weights, so that we can handle. And then we need the specific volume, and the specific volume comes from the Peng-Robinson equation of state, which is shown here, cubic equation in specific volume. And we know everything else here except specific volume. So again, we have our double lines on the edges, which means that this is an implicit nonlinear algebraic relationship that needs to be solved for specific volume. So we have two of these, and we will deal with that in a little bit about how we go about doing that. And then additionally, a move that we make here is that we need the viscosity here, and so the dynamic viscosity. So what we do is we use the assumption that the intrinsic viscosity is a constant, and then we multiply that by a changing density to get the dynamic viscosity, and it's shown there as mu. So there's some additional basic data that we need to come up with here, and we will get that for you. So let's focus for a moment on these two nonlinear relationships and look at them on a separate slide here. And so here what we've done is we've taken the enthalpy balance, moved everything to one side of the equal sign, and then indicated that we have a nonlinear function in temperature that needs to be solved. And then likewise, we'll take the Peng-Robinson equation of state and subtract the right-hand side from both sides and end up with a function equal to 0, and we need to solve that function for the specific volume. And we need to do that at every step of the numerical solution for the problem. So in considering these, we could go back and take a look at one of the methods that we introduced in the second boot camp, such as bisection or the Brent method. Those require two guesses, and they're a little bit awkward to use for this situation because we have to have two initial estimates that bracket the solution, and as we move through the reactor, the solution is a moving target. Also, because we're going to be doing this hundreds and perhaps thousands of times during the solution, we need a method that is very efficient. So what we choose to do here is to take a look at what's called an open method and not a bracketing method. And we start by considering Newton's method, which I'm pretty sure you've seen before, for solving a function of an unknown x. And here, Newton's method is given by this formula, where the k is the iteration starting with an initial value, k equals 0. And so this formula is repeated until it converges to the solution. Convergence being that the next x is virtually equal to the last x. The picture of this is shown on the right, where we have an unknown function and we're interested in determining where that function crosses 0. So we start with an initial estimate, and using the slope here, or the derivative at this point, we project this to the 0 line, and that gives us our next estimate, in which case we'd come up here and get the new derivative and project that to the 0 line, and very quickly we would converge upon the solution. And convergence we would judge here in a relative sense by taking the last change in x over the new x and waiting until that is less than some small tolerance, for example, 10 to the minus 7. Now, the only difficulty here is that it may be a little bit difficult for us to come up with an analytical version of the derivative, all right? And especially if we look up here where CP average here is a function of temperature in a lot of repeated fourth or fifth order polynomials. So an approximation can be used very frequently, which is called the modified secant method, and it's directly based on Newton's method. And what we do is we do not try to derive the derivative of f of x, but rather we approximate it using a small delta or perturbation in x at our particular point of estimate, and x is a small deviation such as 1 part in 10 to the 6th of x or 10 to the 7th. And this gives us a good estimate for the derivative. So we substitute this into the Newton's method formula to get the modified secant method formula, where the denominator becomes this difference here, and then this delta moves to the numerator and sits here. And it's also known that in some situations, although it can converge very rapidly, that the Newton's method it has a tendency to be unstable. So a fix that we make to this at times is to put in a decelerator factor here, which is between 0 and 1, which says, don't take all of the change suggested in x, but take a fraction of it in order to stabilize the solution. It turns out that we do not need that in the case of this particular model, so we can move on and show you how we implement that in the solution. So we've got the full model, and the solution script is going to be more complicated, but a good number of elements are common to what we showed with the simplified model. So let's go back to our Spider editor and now look at the main script. And here it looks very similar at the front end to what we had before. In fact, it's identical. But now our routine that computes the derivatives is called PBR full. And we have another routine here called find T, which is the one that solves the enthalpy balance for temperature. So we come down through here, looking the same as before, and again the same as before, but then we get down to the point of establishing our initial conditions, and so we get the mass flux, all right? We compute that kilograms per second per cross-sectional area meters squared, and that's the mass flux according to the air gun equation, as if the packed bed reactor were empty, and that is a constant. And then we have our feed temperature. We calculate then our initial feed enthalpy, all right? And then this gives us three initial conditions, all right? Feed pressure, and initial enthalpy. And then we come through and do the same that we did before with establishing these V-span and V-eval. And then we calculate solve IVP again, but here we have a little different array of arguments that need to be passed through. And then we'll come back to this and look at how we unpack the results a little bit later and generate plots. It's very similar to what we did before, and we'll look at that. But first, what we want to do is go to the PBR full routine and see how we come up with the needed derivatives. So here, what you'll notice is that even though, well, first we unpack the first two Y's here with the nitrogen and with the pressure from integrating the air gun equation. But then we have a third Y, which is the enthalpy, and that remains constant. So what we've got there is essentially a derivative that's equal to zero, so that stays constant through the solution. Here we've got the stoichiometry and total flow just as before. We've got the partial pressures, but now the pressure is not constant. It comes from the solution of the air gun equation. And then we come down, and now the temperature, instead of coming from integrating a differential equation, it now comes from solving the enthalpy balance. And this is done using a routine called find T, and that implements the modified secant method to solve the enthalpy balance for T, and we'll show you that in a moment. And again, you can see that it's made modular, so it's in a separate function. Here, this represents our reaction rates just as before. Here is our derivative for nitrogen, which is identical, but then things change a little bit toward the bottom here. We have our average molecular weight directly from the information flow diagram. And then the gas density. And again, this was from we got the gas density by solving the Peng-Robinson equation for the specific volume. Let's see if we can pop back to that. Come back here. Let me back up a couple just to remind you. We get the gas density, average molecular weight by specific volume, and the specific volume comes from solving the Peng-Robinson equation of state. So what we're doing here is we're setting up all the parameters for the Peng-Robinson equation of state according to that earlier slide showing how we come up with the mixture coefficients. And then we go and get the specific volume, all right, from a separate routine that we will show you, all right, given all of this information here. And then the gas density is the average molecular weight over the specific volume. And then we have the viscosity being the intrinsic viscosity times the density of the gas. That leads us to forming the differential for the Ergun equation, and then with the heat of reaction, all right, we can put together what the derivative is. The third derivative is for the enthalpy, which will naturally be equal to 0 because of the way we've gone and solved this. So that is what we have here. And let's come back now and take a look at the elements that go together. First, the heat capacity function is the exact same one that we used for the simplified model, so that's identical. But then for the heat of reaction, it's more complicated because now what we do is we include the effect of pressure. So the first part of here is exactly the same down to this point here of computing the heat of reaction based only on temperature, all right? But then we have arrays of critical properties. We have an omega array here. This goes back to that slide that showed you how we were getting the change in enthalpy due to pressure. We have a reduced temperature in kelvins by critical temperature, and we do this for each one of our components. Here we convert the pressure to the critical pressure. We convert it by multiplying by 101.325 kPa per atmosphere. And then these correspond to our B factors, all right? According to the equation. And finally, our enthalpy is given by this, the pressure enthalpy. And then what we can do is we can add the temperature-based enthalpy to the pressure-based with the dot product with H with the appropriate stoichiometry, and that gives us the overall heat of reaction. So a little more complicated, but that's what we do to include the pressure effect on enthalpy. And then we have two more. One is how we go about finding the temperature. And we find the temperature here with this fine T function. And the fine T function takes advantage of something called the FH function, which is the one that calculates the enthalpy balance and provides an error if it's not satisfied. So we come down here and we have a while loop, which what it does is it implements the modified secant method. The delta that we use is 0.1 degree. And so this is the equation for the new temperature based on the old temperature. All right. And you'll notice it's the function itself, and here's the delta, and it's divided by the function minus the function at the modified temperature minus the function at the current temperature. And then we check to see if we've met the tolerance. If so, we break out of this loop. Otherwise, we make a new T1 and we continue the loop. And when it needs to know a value of the function, of the enthalpy balance, it uses this function up here. So that's the one that implements modified secant method to come up with the temperature according to our original information flow diagram. And then the spec volume function is the one that solves the Peng-Robinson equation of state. And again, the Peng-Robinson equation of state is an internal function here that just calculates the pressure minus the prediction of pressure to get the error, and we want to drive this error to zero. And the spec volume implements what we saw on the slide, all right, for the mixture coefficients A and B, all right, mixture coefficients A and B, and then it comes down and it goes through another modified secant method. Again, here we're using the delta as 0.001 times V1, and then that is what comes out with our loop, and the loop will iterate until we satisfy the tolerance requirement. So that gets our specific volume. Having the specific volume, we can move through here as we did, get the density and get the viscosity, and then we have the derivative for pressure, and we can use that to solve the equation. Again, as we're going through and debugging this, we can put breakpoints at any point, stop, look at our variables and see what their values are. And if we notice something that's unusual, we can check it out and possibly make corrections. So as we come back now for our main script and we execute our main script, we'll see that we get similar plots as we had before. This is the temperature profile plot, all right? And if I go back momentarily, it shows a temperature of 376.4, and our simplified model had a temperature of 376.3. It only differed by 1/10 of a degree, so that we didn't gain much there based on the enthalpy balance and based on relaxing constant heat capacity. We only see a difference of 1/10 of a degree. So that sort of indicates we didn't really need to do that. If we look at our next plot, we see the fact that our pressure profile in atmospheres starts at 150 and it goes down to 144. So the pressure through the reactor drops about 6 atmospheres, all right, on 150. So that gives you an idea. A 10% drop would be 15. So this is less than a 5% drop in pressure, but it is measurable, all right, what the air gun equation gives us. Our molar flow profiles look similar to what we had before in terms of how things proceed. I think they may flatten out a little bit earlier in the reactor than they did with the simplified model. And then we look at our conversion, and our conversion profile looks somewhat similar. The conversion here is 21.4%, and our simplified model, the conversion was 22.1%, or 0.7% less than the simplified model. So perhaps that is a little more significant in considering, okay? So let's come back over to the slides, and we already went through these 2 slides. And then we have our ammonia full model that we looked at. And one of the things you'll notice in many cases when we put in a quantity, we put in with a comment on the same line what the units are. Of course, it's essential that you maintain consistent and correct units throughout a script, and the comments can help you with checking that. And also we have all our dimensional quantities here and operating conditions. And then we come over to the block of code here that solves the differential equations. Now let's go back and look at the code over here that unpacked the results. So here's our solve IVP. We get the individual volume array from the T value, T array in the result object. And then we get our nitrogen flow. We can get the hydrogen and ammonia by using array formulas based on the result for the nitrogen flow, the pressure, and we get the enthalpy here, which we expect to be constant. And then we can come down and say, you'll notice we don't have the temperature, but we'd like to see the temperature profile. So what we do is we come down and establish an array the same length as the number of volume points we have. And then we do a for loop to calculate and fill the temperature array based on using, again, the find T function. And that's why we included it at the top of the script. And then getting the conversion is the same as before. And then we have our plots, all right? And we have our exit conditions displayed. So that's how we did that. And that's what's shown on this slide. And then this is the first part of our function that computes our derivatives. And this is the second part. And we went through all that with you. And then this is the function that finds the temperature based on using the f of h function, using the modified secant method. Here's the same heat capacity function as before. And this is the function that solves the Peng-Robinson equation of state for the specific volume, again using the modified secant method. And then this is the heat of reaction, including the effect of pressure on enthalpy. And then here are our temperature and pressure profiles, which we already discussed. Here are the molar flow profiles and the conversion profile. And it shows here on the slide are these results compared to the results that we obtained with simplified model. Okay, so that pretty much brings us to the end of the first example for a packed bed reactor. After a break here, we're going to go on and we're going to take a look at a second case study example, which is shown here. And this one is taken from the Fogler text on chemical reaction engineering, one of the most common texts used to teach chemical reaction kinetics. And it's for cracking of acetone to make ketene with a byproduct of methane. And we'll come back and we'll get into this particular reaction system because it's quite a bit different than the first case study that we did with ammonia. And so it will illustrate different techniques that we bring together in order to solve a more complicated problem. So we'll take a break at this point.